Thank you very much, and thanks a lot to the organizers for this opportunity. So I'm going to talk about the plane partition model. Some of the people in the audience know it very well, but I assume there might be some people who have not seen it before, so I'm going to go slow with the introduction. So what are plane partitions? Well, take a portion of the square lattice, a rectangle of size a and bn, and fill it with integers, non-negative integers, which are weakly decreasing in these two directions. And those are called plane partitions. There's a nice way to visualize them. Just draw the graph of this. Think of this as a function, draw the graph of it. And when you do that, you basically get a stepped surface. So one way you can think about this is that you have a room. All these numbers were 0, then you would have an empty room. And then now you have these integers, and you can stack boxes on top of these cells. The number of boxes that you put is equal to the integers that you have there. And if you look at this, then you can see that you can think of this as also a tiling of a region by 3 different types of rhombi called lozenges. We're going to talk about a slightly more general version of this model called skew plane partitions. So you get skew plane partitions if you basically take a Young diagram, so staircase shape, and just cut out from the corner of the room, and then do the same thing. Put non-negative integers in the rest of your rectangle, which again have the weakly decreasing property. And you can again visualize this by just thinking of this as stacks of cubes. And if you want to think about this as lozenge tilings, then basically what you have is the numbers that you put here are finite. So and these horizontal lozenges are not going to go up infinitely high, but the boundary condition here, it basically corresponds to some boundary condition up at infinity. So these are the objects, and put some kind of probability measure on them. So if there is no height restriction, then the number of configurations you have is infinite. So you can study something like what's called a volume measure. Basically say the probability of a configuration is proportional to some parameter q raised to the volume of your configuration, where the volume is just the sum of the integers that you had. Or if you think about this as a bunch of cubes, so just to take the volume of all those cubes, where each cube has volume 1. A slightly different way to think about this is that you associate weight q with each box, and then the probability of a configuration is just equal to the product of all the weights associated to all the boxes. If all the boxes have the same weight q, then basically what I'm doing is I'm just writing q to the volume as a product of q's, where the product ranges over volume many different cubes. And so this is I'm saying probability of a configuration is proportional to this. Of course, to get the probabilities, you have to normalize this by what's called the partition function, which is just the sum of all the weights over all possible partitions. In the case where you restrict the height, you give a number of you put a restriction on how high the configurations can be, then you can take q equal to 1, then you get the uniform measure. But if the height is not restricted, then q should be strictly less than 1. So this is the model. And you want to study the scaling limit of this model. I've been a series of works doing this for plane partitions. Basically, what you can do is you can say, OK, let's fix a and b. So those are the proportions of the box. Let's n go to infinity. So the boundary grows. Now you have this parameter q, and you could ask, how should this q behave? Q had to be between 0 and 1. If you fix q to be strictly between 0 and 1, then you can compute the expected size of the volume of your configurations, and it will be finite. So it's not an interesting limit to consider in some sense. So if you want your system to grow, then you should have q go to 1. And you can compute what is the right rate. And you can see that the right rate should be that q should go to 1 as e to negative some constant over n as n goes to infinity. And in a skew plane partition version, you also have this Young diagram that you're cutting out from the corner. And you could say, how should this behave? And it can converge. Even though the discrete level, it's just some piecewise linear curve of slopes plus or minus 1. In the limit, you can have it converge to any one Lipschitz function. And you can study various limits. And the most general case that has been studied is that when this cutout converges to some piecewise linear function of slopes anywhere between -1 and 1. So you get something like this. So you have a rectangle. You have removed some piecewise linear curve from it. The slopes can be anything between -1 and 1. And so you think of a room with that as the back wall. And then you can look at random plane partitions in this. And as you can see, so this is basically a bunch of small boxes. The width is about 2,000. So you can see the tiny boxes. And you can see that this model exhibits the Arctic curve phenomenon, where you have some kind of a region, or the phase translation phenomenon, where you have some kind of a region where things look random, and then outside of this region, things look non-random. So you have these frozen regions where, if you look at, say this region, then you only have one type of tile appearing. If you think about lozenge tilings with probability 1, here you have a different type of tile appearing, and so on. So you have these frozen regions, and then you have this curve separating the frozen regions from the liquid regions where the randomness still remains in the limit. So you have this curve, the black curve, which separates frozen regions from liquid regions. And what you want to do is you want to understand this curve, and you want to understand the features of it and the randomness that appears inside the curve, along the curve, and so on. To understand the randomness, what you should look at is, one way to do that is to look at correlation functions. So if you look at these configurations, it's not hard to see that if you know where the horizontal tiles are, then you know the whole configuration. And so to describe randomness, you can just describe what's happening to the horizontal tiles. So you can pick a point and pick some positions for the horizontal tiles and ask what is the probability of seeing horizontal tiles at those positions. Those are correlation functions of the horizontal tiles. We'll denote them by rho. And we're going to study the randomness, the fluctuations, by looking at the asymptotics of these correlation functions in the scaling limit of the system. And this has been done by taking asymptotics of this. So Rochester in their original papers show that this actually process that you get is the determinable point process with a correlation kernel that can be written in this form. And by studying asymptotics of this kernel in various regimes, you can get results that say, for example, in the bulk, you get a point process which is given by the incomplete beta kernel. And so you have the area process along the boundary. There are cusps that can appear. You get the Piercy process there, and so on. Just look at a point here where you have some kind of a different feature, and it has been studied. But most of my talk is going to concentrate on a point that I haven't drawn here. So if you look at the frozen boundary, it touches the rigid boundary at some point. So you have a point here, for example, where this Arctic curve touches. This is called a turning point. And the talk is going to be about the processes that appear at these turning points. And so what you have, what you have at these turning points is, this is a frozen region where one type of tiling appears, one type of frozen region appears. This is a frozen region, tiny frozen region here, where a different type of tile appears with probability 1. And then you have this liquid region, so all these three regions meet together at this point. And in a paper from 2006, Rochester conjectured that the processes that you get at these turning points should be what's called the Dewey corners process. So let's look at those points more carefully. So we want to see what happens at the edge, and we're going to look at the horizontal lozenges only. So let's look at the very first slice. The very first slice is going to have exactly one horizontal lozenge, the one marked with red dot. The next slice is going to have exactly two horizontal lozenges, the green ones. And if you look at the geometry of this, well, the red one has to be in between the green ones. So if I record the positions of the position of the red one is x11, the positions of the green ones are x1, 2, x2, 2, x1, 1 has to be in between x1, 2, x2, 2, and so on. If you look at the third slice, there have to be exactly 3 horizontal lozenges, and the green ones have to be in between those 3 blue ones. In other words, you have interlacing between slices. And so what the Kuhn-Gawrowski decided is, let's look at the joint distribution of the first, say, k slices. And they said that this should converge to the Dewey corners process. What is that process? So if you take an n by n Hermitian matrix from the Gaussian unitary ensemble, if you look at corners of a Hermitian matrix and look at the eigenvalues, so for example, if you look at the 1 by 1 corner, 2 by 2 corner, 3 by 3 corner, and so on, look at the eigenvalues, you have 1 eigenvalue here, 2 eigenvalues here, 3 eigenvalues here. It turns out that if you take, say, a k by k corner and the k plus 1 corner, then the k eigenvalues here will lie in between the k plus 1 eigenvalues here. In other words, you again have interlacing between the 2 different layers, or 2 different corners, neighboring corners. And so what you can do is you can look at the first, say, k corners, and look at all the eigenvalues of the first k corners. You get this triangular system of eigenvalues. You have interlacing between them, and the joint distribution of these this eigenvalues is called the Dewey corners process. And the conjecture of Okunkov and Mkrtchyan was that if you look at the processes that appear at the edge of these lozenge tilings, if you center and scale them appropriately, then as the size of the system grows, this should converge to the Dewey corners process. So they conjectured this, and in the same paper, they actually proved this in one case. So they proved this in the case of plane partitions, when the measure is the q to the volume measure, and this back wall, this lambda, grows as a piecewise linear curve of slopes plus or minus 1. They said, if you look at the joint distribution of what's happening near the edge, center it, so subtract n times a constant, scale it, by square root of n, then it converges to the Dewey corners process. So first, I'm going to show you a joint result with Leonid Petrov, where we show that this actually happens quite generally. And then I'm going to, when you look at q to the volume measures, and then I'm going to look at different regimes. The title of the talk is Plane Partitions with Periodic Weights. So we're going to modify this measure where we're going to give different weights to different boxes depending on their position. And we're going to see what happens to this Dewey corners process at the turning points. So first, the kind of the positive result. So we're going to consider things, regimes like this. So we are interested in the asymptotics of the processes near this turning point. And so what we're going to do is we're going to say, well, let's think of a region like this. Let's have a slice here, and let's specify what's happening to this slice. So you have a bunch of horizontal lozenges on a slice here, macroscopically away from this point, and let's specify the behavior of that slice. For example, maybe specify how the density of the horizontal lozenges changes along this slice, and have a set of have some boundary conditions which grow in a deterministic way along this, and ask what happens at this turning point. So basically, we're going to look at regions like this. We're going to specify the behavior of these green horizontal lozenges along this edge, which is distance n away from this boundary, and n is going to go to infinity. We're going to specify the behavior of this edge. We're going to study the point processes that appear over here. And so it's again the same picture. So you have distance n away, you have n horizontal lozenges here, specify how they behave as n goes to infinity, and study what happens here. So the result that we proved with Leonid Petrov is that if you have some kind of a function, which you can think of this, so this has to be only some weakly decreasing function, which is not constant. And you can think of this, if this was differentiable, then its derivative would basically give you the density of the particles along this edge. You can have arbitrary function like that, specifying what's happening at the edge. Then if you look at the q to the volume measure, when q, again, grows like e to the negative some constant over n, send n to infinity, look at what's happening at the turning point. So look at the first k slices, center the positions of the horizontal lozenges, scale them by square root of n, it's going to converge to the Dewey corners process. if you set gamma equals to 0, then Q becomes 1. So you are basically now we get the result for the uniform measure. This was proven earlier by Vadim Gorin and Greta Panova. And Jonathan Novak later gave a different proof for the uniform measure. In the very special case of the hexagon, this was obtained earlier by Kurt Johansson and Eric Nordenstein. Okay, so this is what happens when you have the Q to the volume measure. But as I said, we're going to modify the measure. So what we're going to consider is measures that look like this. The probability of a configuration is a product of some Q to the I raised to pi I, where you have these parameters Qi, which behave as follows. So basically, earlier I said we're going to give weight Q to every box. Now the weight of the box is going to depend on which vertical slice it falls on. So the weights of the boxes on the first slice are going to be Q1. The weights of the particles boxes on the second slice are going to be Q2, and so on, Q3. So you can have this sequence of weights, Q1, Q2, Q3, and so on. And the probability of a configuration is again going to be the product of all the weights associated to all the boxes. We want to study how this system behaves as it grows. We have to specify what happens to these parameters Q. So there are too many parameters Q, so in this generality it's hard to do something. So what I considered is when these parameters Q are periodic. So fix some period K, finite period K, and take these weights Q0, Q1, Q2, and so on to be periodic with period K. And this was something suggested by Rick Kenyon. So now you could still ask the question, what kind of scaling limit should be studied? So before, the scaling limit that makes sense was that when this parameter Q went to 1 from below. The Q's had to be below 1, otherwise the measure didn't make sense. But Q's shouldn't stay less than 1, otherwise the system has finite expected volume. So you should have Q go to 1. So what you could do here, you could say, okay, we have this now K parameters Q, and we could still take the limit when these parameters Q go to 1, perhaps at different rates. But it turns out that if you study this, then the system doesn't exhibit any new behavior. Basically, what you can do is you can essentially replace all these Q's by their geometric average, and the system essentially behaves the same way as before. So what you want to do is you want to have some of these parameters Q which are bigger than 1, some less than 1. But in order for the model to make sense still, what you should have is that their product should still be below 1. So consider things like this, where Qi is some alpha I times Q. Q is a parameter between 0 and 1. And make sure that the product of these alphas is 1. So if Q is less than 1, then the product of all the Qi's will still be less than 1. And consider the limit when Q goes to 1. And study that asymptotics. So you have the product of the alphas is 1, and Q goes to 1 from below. But it turns out that because we're looking at this unbounded plane partitions, so our configuration space is infinite, this turns out to be problematic. And so to demonstrate that, let's look at first the two periodic case. So consider weights. So the weights I'm considering is some, as I said, alpha 1 Q, alpha 2 Q, but alpha 1 times alpha 2 should be 1. So essentially, I'm looking at the weights alpha Q, 1 over alpha Q. So now what happens? Well, so I have some parameter alpha bigger than 1. So to every box that's over here, we're associating weight alpha Q. So Q is close to 1, so it's basically the weight is going to be close to alpha. But what that means is that if I have a stack of boxes here, say of size 6, then the weight associated to this stack is going to be alpha to the 6. So it grows exponentially. The weight of this configuration grows exponentially. That means that the partition function is going to be infinite, so the model isn't going to make any sense. You could say, okay, well, that's because I put this weight bigger than 1 in this corner. I could fix that by just making sure that this Q over alpha weight goes here. But that doesn't solve the problem, because now if you look at configurations like this, the product of the weights here is going to be alpha Q cubed. And so again, the probability of this is going to be alpha Q cubed raised to the 6. Again, the weights of these things grows exponentially fast. So again, the partition function is infinite. and say, okay, let's cut out this region that's causing trouble. Of course, that doesn't fix the problem. But turns out that this is actually not that bad. You see, because the whole weight of this thing is now, again, there's one extra alpha than 1 over alpha. So the whole weight of this is going to be something like alpha q to the 7. So if that strip that you're cutting out has width m, then the whole weight of that strip is going to be alpha times q raised to the m. But remember that q grows like e to the negative some constant over n. So if you could have this m grow at the scale n, then you could have this whole thing be less than 1. And that turns out to fix the issue, and you have a model which you have a probability measure which is well defined. So basically have a region that looks like this. You've just cut out this corner. You just have to make sure that this is wide enough, and then the measure makes sense. And so you can study the asymptotics of this. So here are some samples. So in both of this, it's the same boundary condition as over here. I'm showing you two pictures. The left one is what you get when you have the q to the volume measure. All the weights q are equal. And this is when you have these two periodic weights. So if you look at the Arctic curve, or the turning points, here you have this one turning point. Over here, actually, this turning point separates into two parts. So the Arctic curve looks like this. Over here, you have this one turning point. Now it separates into two parts. And what that means is that if you look at the point processes at the turning points, you're not going to have this GUE corners process anymore. So, so these two turning points that you see, they're actually separated by a frozen region, which is a frozen region where two tiles appear in a deterministic pattern. So this is the frozen region that separates them. And so if the weights are alpha q 1 over alpha q, then as alpha goes to 1, these two turning points are going to merge, and you're going to have this situation. But the larger alpha is, the farther apart these turning points are going to be, and they're going to separate it by this frozen region. In particular, this means that, so if you look at the turning points processes, what did we have? So we said, if you look at the first slice, there's going to be one particle. And then on the next slice, we're going to have two particles. On the next slice, we're going to have three particles. And we're supposed to have the GUE corners process at the turning point. But now, these particles have to split between this turning point and this turning point. So what you end up having is they're somehow separated. So if you look at the number of particles you have near, say, the top turning point, the number of particles end up being like this. And the number of particles on the other turning point, near the other turning point, end up being like this. So you can't have the GUE corners process anymore because you don't have the right number of particles. But it turns out that the GUE corners process is still there. So if you pick, say, all the odd slices, then you have the right number of particles. The first slice you picked has one particle, the second slice you picked has two particles, the third slice you picked has three particles, and so on. And it turns out that if you look at the distribution of those things, then it's still a GUE corners process. And if you look at these ones as well, it's again the GUE corners process. So what you have near these turning points, is a pair of GUE corners processes which are non-trivially correlated. And okay, so that's what you get if you have two periodic weights and you're studying this regime where you're cutting this out. So many of you saw me discuss this a couple of years ago. Yes?
Obvious why they're even interlaced.
It's not actually, yeah. Before interlacing was a geometric condition. Now it's not a geometric condition anymore. So at the discrete level, they don't have to interlace. That's right. So basically, yeah, this particle has to be between these two. But there is no reason why it has to be lower than this. But asymptotically, it ends up being lower than this. So asymptotically, they do interlace. But before asymptotics, they don't have to. So this was a way to make two periodic weights work. But unfortunately, this method doesn't work if you have your weights periodic with higher period. So basically, this trick of basically cutting out these corners cannot be made to work if the period is higher than 2. It's just it's impossible to do it. So you have to do something else to make to have a measure. And so, well, what was causing the problem? The problem was coming because we were ending up having this weight over here for configurations which are kind of at the corner, which was bigger than 1, and that was blowing up the partition function. But we're interested, if you're interested in studying what's happening at the turning points are far away from this middle slice, so they shouldn't really care what happens at this middle slice. So one way you can make sure that your partition function is finite, which shouldn't have an effect at the turning points, is just have this middle slice have some extra damping weight, which makes sure that the partition function is finite. So if you had these alphas, which were basically, you had the weights alpha 1, alpha q1, q2, q3, q4, and so on, which grew like the alphas. Just look at all the alphas which are less than 1, take their product, and multiply the weight on the middle slice by that. So you're basically studying periodic weights where the weights are periodic everywhere except this middle slice. This makes the partition function finite. And so if there are some samples that you get when you have those kind of weights, so this extra damping weight that you have introduced in the middle makes sure that this limit surface that you get is actually not differentiable anymore along this middle slice. And locally, you get some non-translation invariant point process along this middle slice. And the Arctic curve here as well at the bottom is not differentiable in this middle slice. And you can write down the point processes along this middle slice. So basically, so it's again determinable point process, and this is the correlation kernel. So what is this kernel? Well, so given slice is T1 and T2, look at this sequence and count, let n T1, T2 be the number of ones in between T1 and T2. And if you look at the sequence, you can see that this sequence is not translation invariant. Basically, there's this one repeating here twice. And the process that you have here is basically the kernel has this 1 minus z times delta t minus this n T1, T2 times 1 minus z over alpha n T1, T2. And in the case when alpha is equal to 1, this all become 1, and this becomes 1 minus z, these two terms combine, and this n's cancel, so you have 1 minus z delta t, which gives you the incomplete beta kernel. So basically, the process that you have here is you had the incomplete beta kernel before. Now this splits into a product of two terms like this, which remember this periodicity, and they notice that this is different in this middle slice, so it's not translation invariant anymore. So this is the process that you get at the middle slice. Yes?
So this integral is probably related to F1 hypergeometric?
Maybe. Yeah, let's.
So if you get better function when you have two factors, then with three factors you get 2F1, I think. But anyway, you're not using it.
No. Yeah, you're going to see. So we're going to see kernels where instead of 2, you have basically k different terms like this for any k when we go to k periodic weights. But in the other cases, basically it's going to be translation invariant over here. But in this is the case when it's not translation invariant. So this is what you see at the middle slice, and you can study k periodic weights with this in this model where you're just putting this extra damping factor on the middle slice, and you get in the bulk, you get again the Trinomial point process with this kernel, where basically this factor 1 minus z has now broken up into a product of k different factors. So these are some other numbers. These are not the alphas, and so on, with some exponents which add up to delta t, and basically they remember the periodicity. Unless if you're away from this middle slice, then what you have is basically a z cross kz translation invariant point process, which is actually a special case of a family of point processes that was studied by Alexei Borodin and Senor Schlossman. They built a 2-parameter family of determinable point processes, and this is actually a special case of the processes that they constructed. So that's what happens in the bulk. What happens at the turning points? So I'm going to take some favorable boundary conditions to study the turning points. So I'm going to have the rectangle to be infinite. And so we have this weights alpha. What you do is you look at the product of neighboring alphas. So let's call them betas. So these numbers, even though your weights are periodic, these numbers with period k, these numbers might have, there might be fewer than k of them. So just look at these numbers, the products of neighboring alphas, and order them. And so let's say there are m different ones. And so it turns out that along the boundary, you end up having exactly m turning points. These turning points, so before you had a turning point, that was one turning point. So now each one is going to separate into m different turning points. And these turning points are going to be separated by frozen regions. Well, the frozen region that you have here at the very top is what you had before. This is a frozen region where one tile appears with probability 1. It looks like this. The frozen region at the very bottom is again a frozen region where one tile appears with probability 1. It looks like this. And in these middle frozen regions, in each one of them you have 2 tiles appearing in a deterministic pattern. And you can specify an arbitrary pattern. So do something like up, down, up, down. You can specify an arbitrary pattern and look at the width. This is width k. Then you can come up with weights which are k-periodic, such that the system builds a frozen region which has this pattern repeating k-periodically. And now if you look at the number of particles that you have near a particular turning point, then the number of particles are again going to be like this. You have a bunch of 1s, so the first slice is going to have 1, the second slice is again going to have 1, the third slice is going to have 1. So the first k slices will have 1 particle, the first m slices will have 1 particle, the next m slices will have 2 particles, and so on. So you get something like this. And so again, this itself is not going to be the GUE corners process, but it turns out that if you pick slices, as long as you have the right number of particles, if you look at the marginal distribution, you're going to have the GUE corners process. So pick any slice where you have 1 particle, any slice where you have 2 particles, any slice where you have 3 particles, and so on. And you look at the joint distribution of the particles on those slices, that's again the GUE corners process. And so this is a sample. So you have this, say this is a 4-periodic sample. So you have these 4 turning points. They're separated by these frozen regions. So this is one tile appearing with probability 1, and then you have these patterns. And what's happening is basically you have these vertical facets, and if you project them to the floor, then you have lines which bisect this 90-degree angle into equal angles. So So you can have any rational slope angle. You can have any vertical slope of any rational. You can have a vertical facet of any rational slope. And you can again compute the point process over here, the joint process of all the slices, and you get a determinable point process with this kernel. So basically, what happens here is this things. So if this was T1 and this was T2 and this was T1, you'd get the GE corners process. But now this thing basically counts. It counts the number of jumps that you see. So if you pick a position T1, instead of the exponent here being T1, it actually counts the number of different integers you have seen up to position T1. And again, as Rick noticed, the interlacing again is not a geometric constraint. It's just asymptotically it ends up happening. So in all these results, said okay, the Okungo-Verstegen conjecture was saying that you should see the GE corners process, and well, in these cases, it seemed like we're getting away from the GE corners process, but not really. It's still there in some sense. There is a regime in which you actually get rid of the GE corners process. So basically, what was happening is when we were considering weights, say alpha q 1 over alpha q, if alpha is 1, then you have one turning point. If alpha is bigger than 1, then that has pulled these things apart, and you have two turning points. You could ask, well, what happens as alpha goes to 1 as the system grows? So somehow alpha is pulling this turning point apart, but if you don't pull it apart too much, then you can have a process which is different from the GE corners process. So consider, say, two periodic weights, alpha q 1 over alpha q, such that as the system grows, so as n goes to infinity, and as q goes to 1, alpha also goes to 1. But alpha should go to 1 slower than q goes to 1. So have alpha go to 1 like e to the some gamma times root r, or where r is 1 over n here. So q was e to the negative, say 1 over n, and alpha is going to be e to the negative 1 over root, or e to the 1 over root n. Again, you have a determinable point process. In the bulk, you're going to get just the z cross z translation invariant ergodic scheme. You're going to get the incomplete beta process. So the bulk is not going to see the periodicity in the limit. But and if you look at the frozen boundary, you again have only one turning point at the edge, but it does remember the periodicity. You get a determinable process with this correlation kernel. So this term, if you put gamma equals to 0, then these two things combine, and you have omega raised to T2, and here you have zeta raised to T1. But now this has split into this term omega times omega minus gamma. And so this is not now the GE corners process is not present here at all. It's some kind of a different process. It's one parameter deformation of the GE corners process. Okay, thank you very much.